Okay, here we go. In part B, the question is, does the series right there converge or diverge? Of course, we're going to use the integral test here. Our series this time, n equals 1 to infinity, n squared e to the negative n. Okay. Well, let's see how this plays out. So for one, you want to define your function, which is just a matter of calling it f of x and turning the variable into x. So f of x is x squared e to the negative x. You probably remember we need to show the three conditions on f of x. Is it positive, continuous, and decreasing for x greater than or equal to 1 in this case? Well, the first two conditions are always just going to be visual. Hey, is that function always positive for n greater than or equal to 1? And I think we'd say, yep, I'm squaring. Even e to the negative exponent is a positive number. I've got a positive times a positive. No question about it. F of x is definitely positive for x greater than or equal to 1. I don't need to do anything else. That'll be fine. I do want to write that, though. Definitely need to write it so people know that I did think about it. Hey, is that function continuous? Sure is. There's no vertical asymptotes. There's no jumps or holes. I never divide by 0. So it's continuous as well. And now here's the interesting part, very interesting part to this question. Is this function decreasing for x greater than or equal to 1? And we don't want to ever directly answer that. We want to show it with the derivative. So we're going to show that the derivative is negative. And that's what I've got on the other side here. So let's see. Our derivative, of course, requires a product rule. 2x e to the negative x minus x squared e to the negative x when we apply product rule. Certainly feel free to do this derivative on your own. It's always good to practice. Keep yourself real sharp. Okay, you know what? I would like to rewrite this. As I showed you guys in the last example, it's really nice to show something's negative when you think of it as a fraction. So if you've got like negative divided by positive or positive over negative, and there's no arguing it. Yep, that's always going to be negative in the end. Since I have these two e to the negative x's, I'm going to rewrite it this way. 2x minus x squared, both over e to the x. Okay, that's really going to be helpful. So let's take a look. Hey, where we begin at x equals 1, right? When x equals 1, is that negative? Wait a second. Hold on a minute. At x equals 1, I've got 2 minus 1 over e. At x equals 1, my derivative is actually positive. Oh. Well, this is terrible. Or is it? The question at this point is, can we still use the integral test? Or do we just need to give up and say this question cannot be answered with the integral test because the function is not decreasing for all x greater than or equal to 1. At 1, it's clearly increasing. It turns out we can still answer this series with the integral test. Let's keep going. Let's move on to x equals 2. I'll show you why kind of as this unfolds. Just go with me for now. Hey, at x equals 2, what's happening with the derivative? Hey, at 2, well, our numerator is 0. Okay, well, that's moving in the right direction, I suppose. What's happening at x equals 3? Now finally at 3, our derivative turns negative, right? I've got 6 minus 9, negative 3 on top over e to the third. And I've got a negative derivative there. And what will happen for every value of x greater than 3? Well, at 4, the numerator is still negative. At 5, the numerator is negative. 6, the denominator is always positive for all of these. It's not until I get to 3 does x squared become bigger than 2x. But then it stays bigger after that, right? So at 3 and larger, it's always going to be negative. Maybe we can even note that. Like x squared is bigger than 2x. Now I've gone off the screen. From that point forward, my numerator is always negative. Sorry, it's a little blurry. Okay, now this is the key. This is why we can still use the integral test. Because although it didn't start happening at 1, it only started happening at 3, but then from 3 and bigger, it always worked. So if it was like kind of jumping around all over the place as high up as we kept counting, then no, we could not apply integral test. If it kept going like 0, positive, negative, 0, positive, if it kept doing that and it never finally settled in and just became negative forever, we couldn't use integral test. But because at 3, the derivative is now always negative, it's always decreasing, we can still use it. Okay, so there's kind of my note. F of x is decreasing, but not starting at 1, starting at 3. We can still use the integral test, but how? Turns out we need to make an adjustment. And I'll see if you can, I'll write it. I'll just put this all out there. I'll give you a moment to write this, and then I'll explain what happened. So I've got the original series here, and then I've broken off the first 2 terms, and then I'm starting up my series again, but now at 3. So what's going on? Okay, the original series. Hey, all this means is that you're adding up all of these terms, right? Well, then let's think, what is the term at n equals 1? Well, 1 squared e to the negative first. At n equals 1, this is the term. Then I'm going to add the second term. At n equals 2, it's 4 e to the negative 2. So there's the n equals 2 term. And then all the infinitely many terms left would begin at 3 to infinity and would keep the same nth term formula, n squared e to the negative n. So I can rewrite it, my original series, this way. Obviously, I stop at 3 because that's where we're decreasing. Now, here's kind of more logic going on. If this converges or diverges, it's completely dependent on if this converges or diverges. Okay? Why is that? Because these are both finite values. So I've got these 2 finite numbers adding on to this. If this is a finite number and I add on 2 other finite numbers, I get a finite number for the whole thing and it converges. So if this converges and I add on a little bit more, this is still going to converge. But of course, if this diverges, it doesn't matter what I add on, it's still going to diverge, and that's going to diverge. So if this converges, well, this will converge to something a little bit bigger because I've got these other numbers to tack onto it. But if this diverges, then that's going to diverge. Okay. Hopefully that makes sense. It's like if you're adding infinity, well, if you add on a few more numbers to infinity, it's still infinity. If it's a finite number and you add on a couple more numbers, it's still a finite number. In the past, this whole discussion here with the beginning of this problem has really led to some really good conversation in the classroom, and people start saying, well, what if this and what if that? Obviously we don't have that here, but maybe if you want to bring like other scenarios to our Zoom meeting time, well, what if that or this? Certainly we can entertain all that. All right. Anyway, I think you get the point for this one, I hope. We know that our function is positive, continuous, and decreasing for this at n greater than or equal to 3 from what we did earlier. So at this point, we have checked the conditions, and we can move on to, gave part of it away, we can move on to the integral. And you notice we're only applying this test. The integral test is only applying to this now. So we're going to start our integral at 3. 3 to infinity, x squared e to the negative x dx. All right, so you look at that, you think, oh man, is it possible to take that antiderivative? Well, I think I gave it away a moment ago, but what technique do we need here? X squared e to the negative x. We need integration by parts. Hey, you could do it the long way using the formula, by all means, but it turns out this is one of the forms that you can use the tabular method. We'll do this by parts with the tabular, and if you remember how that plays out, here's the tabular. Draw this up a little bit at this point. Okay. We denote the sign, positive or negative, starting with positive, they alternate. What would have been u? Well, we're going to take the x squared. What would have been dv would have been e to the negative x dx. And tabular says, okay, for the sign alternate, what would have been u, you take derivatives until you hit 0. That tells you where to stop. What would have been dv, take antiderivatives and fill it all out. Then that will be the first term in your answer. This will be the second term in your answer. This will be the third term in your answer. And I think that's where I pointed my arrow, right over here. Right, the first term, negative x squared e to the negative x, minus 2x e to the negative x, minus 2 e to the negative x. From our tabular method, of course, we're going to take that from 3 to t as t goes to infinity. All right, so far so good. Plugging in, oh boy, woo, I think I just need to pull it over here. Plugging in the t, and you notice I have tucked those underneath as e to the t. I don't think that's really, I gave them negative. Okay, there we go. Negative t squared over e to the t, 2t over e to the t. I don't know why I did this. I think using the negative signs is fine. But that's what I decided to do. And then plugging in 3. Okay, I've got all of these. Sorry, it's a little bit fuzzy. Let me pull that over a little bit. All right, so I think I'm understanding my own thinking now from the past. I wrote these all as fractions in order to make this limit more clear, although I think some of them are clear enough. Let's start with the simplest one. Hey, where's 2 over e to the t going as t goes to infinity? Well, clearly 0, right? But the others, infinity over infinity, infinity over infinity, here's what I'm saying here. All right, 0, no problem. but both of those are indeterminate. We're going to need L'Hopital's rule on both of those guys. And so you see my next line here. And apologize if I'm going a little bit quickly. That's a lot to write. I'm applying L'Hopital's rule on this, negative 2t over e to the t. I'm applying L'Hopital's rule there, negative 2 over e to the t. This one went to 0, of course. And all of these became negative 17 e to the negative 3, and it was subtracted, so plus 17 e to the negative 3. We're still taking the limit. Hey, now after L'Hopital's rule, I can tell this goes to 0, but that one I'm going to need L'Hopital again. And that's what I've got on the next page. Applying the L'Hopital again brings me to here. And I've still got that plus 17 e to the negative 3. Now I can tell what's happening there. It's going to 0 as well. And so this whole thing simply goes to 17 e to the negative 3. This is my integral. I can tell that my integral converges. And hey, if my integral converges, the real question, of course, this whole time was about the series. I know that that original series converges by the integral test. If you really wanted to, we kind of already talked through it, but this really just showed that the series starting at 3 converges. But then we can immediately imply that the series starting at n equals 1 converges. We already showed that logic back before. So let's just state it here. The original series, n equals 1 to infinity, converges by the integral test. Now, one thing people sometimes mistakenly do, and I try not to mention mistakes very often because it gets in your head, but because it happens quite a bit, I think I'll go ahead and say it. Do we know what that original series, what was that original series? N equals 1 to infinity, was it n squared e to the negative n? Do we know what that converges to? Do we know exactly what all of these add up to? No, we have no idea what those numbers add up to. All we know is that it converges. Now, some people might say, mistakenly, hey, this is the answer to the integral, and before we said this, so shouldn't we just put the 17 e to the negative 3 here and then add those two numbers on and we'll know what this adds up to? No, absolutely not. We have no idea what this adds up to. All we know is that it converges. The integral added up to this, but the integral is based on a function, a continuous function. A series is just individual points. We have no idea what the series adds up to. All we know is that it converges. We don't know what to. Okay, so just because so many people make that mistake in logic. All right, that's it. We're going to stop this video here. We're going to talk about the P series next.